Good morning, everyone. I am Moni from PSC Chemistry Honors first year. Today I am read a chapter as block. The S block elements of the periodic tables are those in which the last electron enters the outermost s orbital. As the s orbital can accommodate only two electrons, two groups belong to the S block of the periodic table. Group 1 of the periodic table consists of the elements lithium, sodium, potassium, rubidium, cesium, and francinium. They are collectively known as the alkali metals. These are so called because they form hydroxide on the reaction with water, which are strongly alkaline in nature. The elements of the group 2 include beryllium, magnesium, calcium, strontium, barium, and rubidium. These elements, with the exceptions of beryllium, are commonly known as with alkaline earth metals. These are also called because of their oxide and hydroxides are alkaline in nature, and these metal oxides are found in earth crust. Among of the alkali metals, sodium and potassium are abundant, and lithium, rubidium, and cesium have much lower abundance. Francinium is a highly radioactive. It is the longest, has a half-life or only 21 minutes. Of the alkaline earth metals, calcium and the magnesium rank 15th and 16th in abundance respectively in earth crust. Strontium and the barium have rarest earth. Its longest lived isotope of the alkaline earth metals, calcium and magnesium, rank of 15th and 16th in abundance respectively in earth crust. Strontium and barium have a much lower abundance. Beryllium is rare and rhenium is the rarest of the all, comparison only the general electronic configuration of a S block element in a noble gas in a noble gas for the alkali metals and a noble gas for NH2 for the alkaline earth metals. Lithium and beryllium in first elements of the group 1 and the group 2 respectively exhibit some properties which are different from those of other members of these respective groups. In these anomalous properties, they resemble the second element of the following group. Thus, lithium shows the similarity to magnesium and beryllium to aluminium in many of other properties. This type of diagonal similarity is commonly referred to as a diagonal relationship in the periodic table. And the diagonal relationship is due to the similarity in ionic size or a charge radius ratio of the element. And the monovalent sodium and the potassium ions and divalent magnesium and the calcium ions are found in large properties in biological fluids. These ions performed important biological functions such as maintenance of ions balance and nerves impulse conduction. Group 1 elements alkali metals. The alkali metals shows the regular trend in their physical and chemical properties with the increasing atomic number. The atomic, physical and chemical properties of alkaline metals are discussed below. Electronic configuration. All the alkaline metals have one valence electron outside the noble gas core. The loosely held s electron in the outermost valence shell of these elements make them it most electropositive metals. They readily lose the electron to give monovalent and positive ions. Hence, they are never found in a free state in nature. Ionization enthalpy. The ionization enthalpy of alkali metals are considerably low and decreasing down the group from lithium to cesium. This is because the defect of increasing size outweighs in the increasing nuclear charge, and the outermost electron is very well screened from nuclear charge. Hydration enthalpy. The hydration enthalpy of alkali metals ions decreasing with increasing the ionic size. Lithium plus has a maximum degree of hydration, and the more the reason lithium salts are mostly hydrated. Physical properties. All the alkali metals are silver, white, soft, and light metals. Because of the large size, these elements have low density, which increasing down the group from lithium to cesium. However, potassium is lighter than sodium. The melting and the boiling point of alkali metals are low, indicated weak metallic bonding due to the presence of only a single valence electron in them. The alkali metals are their salts impact characteristics color to an oxidizing flame. This is because of the heat from the flame excite the outermost orbitals electron to the higher energy level. When the excited electrons come back to the ground state, there is emissions of radiation in visible region of their spectrum as given below. Alkali metals can therefore be detected by the respective flame test and can be determined by flame photometric or atomic absorption spectroscopy. These elements, when irradiated with light, the light energy absorbed may be sufficient to make an atom lose electron. This is the following table 10.1 atomic and physical properties of alkali metals. The property makes a cesium and a potassium useful as an electrode in a photoelectric cell. Chemical properties. The alkali metals are highly reactive due to their large size and low ionization enthalpy. The reactivity of these metals increasing down the group. Reactivity towards air. The alkali metals transition is dry air due to the formation of their oxide, which is turned to react with moisture to form hydroxide. They burn vigorously in oxygen, forming oxide, lithium from monoxide, sodium from peroxide, and other metals from superoxides. The superoxides O2 ion is stable only in the presence of large cations such as KRB and SCS. In all these oxides, the oxidation state of the alkali metal is +1. Lithium shows the exceptional behavior in reacting directly with nitrogen of air to form nitrides, Li3N as well. Because of this high reactivity towards air and water, alkali metals are normally kept in kerosene oil. Reactivity towards water. The alkali metals react with water to form hydroxide and dihydrogen. It may be noted that although lithium has most negative electrophile value, its reaction with water is less vigorous than that of sodium, which has the least negative value among of these alkali metals. This behavior of lithium is attributed to the small size and very high hydrogen energy. Other metals of the group react exponentially with water. Reactivity towards dihydrogen. The alkali metals react with dihydrogen at about 637 Kelvin to form hydrides. Reactivity towards halogen. The alkali metals readily react vigorously with the halogen to form ionic halides. However, lithium halides are somewhat covalent. It is because of the high polarization capability of lithium ion. The distortion of electron cloud of the anion was called the polarization. The lithium positive ions is very small in size and has a high tendency to distort electron cloud around the negative halide ion. Reducing nature. The alkali metals are strong reducing agent, lithium being the most and the sodium the least powerful. The standard electrode potential with measure the reducing power represent the overall charges. Sodium in liquid ammonia. The alkali metals dissolve in liquid ammonia, giving deep blue solution which are conducting in nature. The blue color of the solution is due to the ammoniated electrons which absorb the energy in the visible regions of the light and thus impart blue color of the solution. The solutions are paramagnetic and on standing slowly liberate hydrogen resulting in the formation of amides. Uses. Lithium metal is used to make the useful alloys, for example with the lead to make the white metal bringing for motor engines, the aluminium to make aircraft parts, and with the magnesium to make the amorphous plates. It is used in the thermomolecular reactions. Lithium is also used to make the electrochemical cells. So sodium is used to make the alloy needed to make the PbE2 These organoletrid compounds were earlier used as an anti-knock additives to petrol, but nowadays vehicles use lead-free petrols. Liquid sodium metal is used as a coolant in the fast breeder nuclear reactors. General characteristics of the compounds of the alkali metals, oxides and hydroxide. On combustion in excess of air, the lithium forms mainly the oxides, and plus some peroxides. Sodium forms the peroxides, whilst potassium, rubidium, cesium form the superoxides. Under appropriate conditions, pure compounds M2O, M2O2, and MO2 may be prepared. The increasing stability of the peroxides and superoxides, as the size of the metal ion increasing is due to the stabilization of the large ions increasing it due to the stabilization of the large ion by large cations of the lattice energy effects. The oxides and the peroxides are colorless when pure, but the superoxides are yellow or orange in color. The superoxides are also paramagnetic. Sodium peroxide is widely used as an oxidizing agent in organic chemistry. Halides. The alkali metal halides, the MX, are all high melting colorless crystalline solids. They can be prepared by the reaction of the appropriate oxides, hydroxides, or a carbonate with aqueous hydraulic acids. All these halides have the high negative enthalpy of formation. The melting and the boiling point always follows the triads, the fluorides, chloride, bromide, or iodides. All these halides are soluble in water. The low solubility of LiF in water is due to its high lattice enthalpy, where the low solubility of CSI it is due to the smaller hydration enthalpy in its two ions. Other halides of the lithium are soluble in ethanol, acetone, and ethyl acetate. LiCl is soluble in pyridine also. Salt of oxoacids. Oxoacids are those in which the acidic proton is an hydroxyl group with the oxo groups attached in the same atoms. Carbonic acids, the alkali metals, form the salt with all oxoacids. They are generally soluble in water and thermally stable. They carbonates and in most cases of the hydrocarbons are highly stable to heat. As the electropositive character increases down the group, the stability of the carbocation and hydrogen carbocation increases. Lithium carbocation is not so stable to heat. Anomalous properties of lithium. The anomalous behavior of lithium is due to the exceptionally small size of its atom and its ion. High polarization power. As a result, there is increased covalent character of the lithium compound, which is responsible for their solubility in organic solvents. Further, lithium shows the diagonal relationship to magnesium, by which have been discussed subsequently. Points of the difference between lithium and other alkali metals. Lithium is much harder. Its melting point and boiling points are higher than other alkali metals. Lithium is the least reactive but the strongest reducing agent among all the alkali metals. LiCl is deliquescent and crystalline as a hydrated. Lithium hydrogen carbonate is not obtained in the solid form, while all other elements from the solid hydrogenate. Lithium, unlike other alkaline metals, form no ethanosides on reaction with ethane. Points of similarity between lithium and magnesium. The similarity between lithium and magnesium is particularly striking and arising because of their small size. Both lithium and magnesium are harder and lighter other elements in respective groups. Lithium and magnesium react slowly with water. Their oxides and hydroxides are much less soluble and their hydroxide decompose on heating. Both of the nitride Li3 and Mg3 and 2 by direct combination with nitrogen. The oxides Li2O and MgO do not combine with excess oxygen to give any superoxides. Both HiCl and MgCl2 are soluble in ethanol. Both HiCl and MgCl2 are dequescents and crystalline form aqueous solution as hydrated. Some important compounds of sodium. Industrial important compounds of sodium including sodium carbonate, sodium hydroxide, sodium chloride. Sodium carbonate means washing soda. Sodium carbonate is generally prepared by Solvay process. In the process, advantage is taken of the low solubility of sodium hydrogenated, whereby it gets precipitated in a reaction of sodium chloride with ammonium hydrogen carbonate. The latter is prepared by passing a CO2 to a concentrated solution of a sodium chloride saturated with ammonia. In the process, NH3 is recovered when the sodium containing NH4Cl is treated with a CaOH2. Calcium chloride is obtained as a byproduct. It may be mentioned here that the Solvay processes cannot be extended to the manufacture of the potassium carbonate because potassium carbonate is too soluble to be precipitated by addition of ammonium hydrogen carbonate to saturated solution of a potassium chloride. Properties. Sodium carbonate is a white crystalline solid which exists as a dehydrated Na2CO3 dotted NH2O. This is also called a washing soda. It is readily soluble in water. On heating, the dehydrated losses in water crystalline to form a monohydrates. Uses. It uses the water softening, laundering and cleansing. It is used in the manufacturing of the glass soaps and it is used in the paper, pens and textile industry. It is important laboratory reagent both in the qualitative and quantitative analysis. Sodium chloride NaCl. The most abundant source of sodium chloride is the sea water, which contains 2.7 to 2.9 by the mass of the solvent. Salt is the tropical countries like India. Common salt is generally obtained by the evaporation of sea water. Approximately 50 lakhs tons of salt are produced annually in India by the solar evaporation. Card sodium chloride generally obtained by crystallization. Sodium hydroxide, caustic soda and NaOH. Sodium hydroxide is generally prepared commercially by the electrolysis of sodium chloride in the Kester-Keller cells. A brinz solution is electrolyzed using a mercury cathode and a carbon anode. Sodium metal discharged at a cathode combined with the mercury to form a sodium amalgam. Chloride gas is evolved at the anode. Cathode Na positive plus electron gives HgNe amalgam. Anode chlorine negative gives half Cl2 plus electron. The amalgam is treated with the water to give the sodium hydroxide and hydrogen gases. Sodium hydroxide is white transculate solids. It melted. It is readily soluble in water to give a strong alkaline solution. Crystals of the sodium hydroxides are deliquescents. The sodium hydroxide solution is at the surface react with CO2 in atmosphere to form Na2CO3. Sodium hydrogen carbonate, baking soda. Sodium hydrogen carbonate is known as the baking soda because it decomposes on heating to generate bubbles of carbon dioxide, and it's in a cake soda pastries and making them light soda volume. Sodium hydrogen carbonate is made up of saturating sodium to sodium carbonate with carbon dioxide. The white crystalline powder of sodium hydrogen carbonate being the less soluble and get separated. Biological importance of sodium and potassium. Sodium ions is found primarily on the outsides of the cell, being located in a blood plasma and interstitial fluids which surround the cell. These ions participate in the flows of the water across the cell membranes and in the transport of the sugar and the ammonium acids into the cell. Sodium and potassium, although so similar chemicals, differ quantitatively in their ability to penetrate cell membranes, in their transparent mechanisms, and their efficiency to activate the enzymes. This potassium ions are most abundant cation when cell fluids, where they activate into many enzymes. Electronic configuration. These elements have the electrons in s orbital of the valence shell. The general electronic configuration may be represented as ns2. Like alkyl metals, the compounds of these elements are predominantly ionics. Atomic and ionic radii. The atomic and ionic radii of alkaline earth metals are similar than those of corresponding alkaline metals in the same period. This is due to the increased number charge in these elements within the group of the atomic or ionic radii increasing with increasing atomic number. Ionization enthalpy. The alkaline earth metals have a low ionization enthalpy due to the fairly large size in atoms. Since in the atomic size increasing down the group, the ionization enthalpy decreases. Hydration enthalpy. Like alkaline metal ions, the hydration enthalpy of alkaline earth metal ion decreasing with increasing the ionic size down the group. The hydration enthalpy of alkaline earth metal ions are larger than those of alkaline metal ions. Thus, compounds of the alkaline earth metals are more extensively hydrated than those of alkaline metals. Physical properties. The alkaline earth metals in general are silvery white, lustrous, or relatively soft but harder than alkaline metals. Beryllium and magnesium appear to be somewhat greasy. The melting and boiling point of these metals are higher than the corresponding alkaline metals. Because of the low ionization enthalpy, they are strongly electropositive in nature. The electropositive character increasing down the group from beryllium to barium. Calcium stronger and barium impact characteristics bricks red, crimson and apple green color respectively to the flame. In a flame, the electrons are excited to higher energy level, and when they drop back to the group state, the energy emitted in form of visible light. Chemical properties. The alkaline earth metals are less reactive than the alkaline metals. The reactivity of these elements increasing on going down the group. Reactivity towards air and water. Beryllium and magnesium are kinetically inert to oxygen and water because of their formation of oxide film in their surface. However, the powdered beryllium advance virality on ligations in air to give the BeO and Be3N2 reactivity towards the halogen. In the alkaline earth metals combine with the hydrogen at elevated temperatures, forming their halides. The thermal decomposition of BeF4 is the best route for the preparation of BeF2. Uses beryllium. It is used in manufacturing of alloys. Copper beryllium alloys are used in the preparation of high strength spring. Metallic beryllium is used for making the windows of the X-ray. Magnesium from the alloy, which is the aluminium, zinc, magnesium, and its magnesium aluminum alloys being light in a mass are used in aircraft construction. Magnesium is used in a flash powders and bubbles in incendiary bombs, and the signals the suspension of the magnesium hydroxide in the water called the milk of magnesia. It is used as an anti-acid in medicines and general characteristics of the compounds of the alkaline earth metals. Oxides and hydroxides. The alkaline earth metals burn the oxygen to form the monoxide, which except form PeO have a rock salt structure. The PeO is essentially covalent in nature. The enthalpy of the formation of these oxides are quite high, and consequently they are very stable to heat. Halides. Except for beryllium halides, all other halides of the alkaline earth metals are ionic in nature. Beryllium halides are essential covalent and soluble in organic solvents. Beryllium chloride has a chain structure in the solid state as shown follows. Salts and oxides. The alkaline earth metals are from the salts of oxo acids. Some of these carbonates of the alkaline earth metals are insoluble in water and can be precipitated by addition of sodium or ammonium carbonate solution in the solution of a soluble salt of these metals. The solubility of the carbonates in the water decreasing as the atomic number of the metal ion increasing. Although carbocation decompose on heating to give the carbon dioxide and oxides, beryllium carbonate is unstable and can be kept only in the atmosphere of CO2. The thermal stability increasing with increasing cationic size. Sulfates. The sulfates of the alkaline earth metals are white solids and stable to heat. The solubility decreasing from CaSO4 to BaSO4. The greater hydration enthalpy of Pe to positive and Mg to positive ions overcome the lattice enthalpy factor, and therefore their sulfates are soluble in water. Nitrates. The nitrates are made by dissolutions of the carbonates in dilute nitric acid, magnesium nitrate crystallization with the 6 molecules of water, where the barium nitrate crystallization as an anhydrous salt. The again show the decreasing tendency to form the hydrates with increasing size and decreasing hydration enthalpy. All of them decompose on heating, gives the oxides like lithium nitrate. The reaction given below. Thank you.